Hello, this video discusses one of the most used rules of differentiation, the chain rule. The chain rule pops up everywhere. The chain rule shows up in many problems, and you're going to have to use the chain rule in conjunction with the product rule and with the quotient rule, and of course, the power rule. We'll begin our study of the chain rule by considering f of x equals 2x cubed plus 3 squared. And of course, we're going to ask, what is its derivative? That is going to be our go-to question. And your initial guess, so I'll put initial guess, might be that this is going to be 2 times 2x cubed plus 3 to the 1 power. The 2 hops down out front, 2x cubed plus 3 to the 1 power, or we could also call this 4x cubed plus 6. This is our initial guess. However, unfortunately, it's not exactly right. It's missing something. It's missing the chain rule. So to see where that chain rule comes from, let's do this derivative a slightly longer way. And then by that, I mean I'm going to square out this term. 2x cubed plus 3 times itself. First times first is going to be 4x to the 6th. Outside times outside is 6x cubed. Inside, so that's going to be 12x cubed. And then plus 9. So I squared out what we mean by f of x. And now to find f prime of x, I just take the derivative and get 24x to the 5th plus 36x squared, which is not the same thing as this. But there's a way to reconcile these two things together. And I'm going to factor this guy. I'm going to factor out a 6x squared. So if you factor out a 6x squared here, you get 4x cubed. Plus, we factor a 6x squared out here, we get a 6. So I pulled out a 6x squared out of both these terms, and notice what's inside here is exactly our initial guess. So we need to make up for it by compensating, by multiplying by this guy. So where on earth, 6x squared, how am I going to find a 6x squared anywhere in this problem, in the original problem? Well, what that is the derivative of the inside of these parentheses. And so, therefore, we're going to discover the chain rule tells us that you take the derivative of the outside, then go inside the parentheses and take the derivative of the inside. The chain rule works with functions inside of other functions. For example, 2x cubed plus 3 is a function inside of another function, the squaring function. So in this case, I can think of the inside function as being 2x cubed plus 3. And then I can think of the outside function, and I'm going to use the letter u, to be u squared. So notice that you take your x, you feed it into the g machine, you get 2x cubed plus 3, you then feed that to the f machine, and you get 2x cubed plus 3 squared. And I broke this down using this u squared. We're only going to do this for the first day or so. After that, we're going to start working without having to write in this middle step. So the idea we just discovered is that for this case, our derivative we just found was, let's see, so we took the derivative of this guy, took its derivative, and we got 2, and then of course we had the inside function, 2x cubed plus 3 to the 1 power, and then we multiplied that by the derivative of the inside function. So the official chain rule is if you take f of g of x and we take its derivative. You take f prime and you plug in the inside function as it is, and then you multiply that by g prime of x. So notice I took the outside function's derivative. The derivative of f is 2u. So I'll put it over here. F prime of u is 2u. And g prime of x is 6x squared. So notice I did 2u. I'm thinking of the g of x as being a u to the 1 power. And then I'm going to multiply that by the derivative of g. So that's f prime of g of x times g prime of x. And this is the chain rule. Leibniz had a slightly different way to write the chain rule, and I'll show you that way as well. So if we're interested in finding the derivative of f with respect to x, how does f change when I change x? This is going to be, how does f change as I change u? And then how does u change as I change x? And in this case, we're thinking of f of u as u squared, and we're thinking of u as 2x cubed plus 3. So really, I guess u and g are actually the same thing. So the derivative of f with respect to u is 2u. The derivative of u with respect to x is 6x squared. But I don't like the u's and the x's being mixed together, so I'm going to get rid of the u and put back in what I mean for u, which is 2x cubed plus 3, and then of course times 6x squared. So this is Newton's notation with the primes, f prime of g of x times g prime of x. Leibniz notation is, how does f change when x changes? We'll ask, how does f change as u changes, and how does u change when x changes? And the advantage of Leibniz notation is, and these are not actually fractions, but you can almost imagine like I'm canceling those two guys out, and I get df dx. So these are not fractions. However, Leibniz notation makes them kind of more intuitively, if we think of them just as fractions a little bit, we can see that this is df dx. The chain rule takes lots of practice. So let's do a couple examples to get good at this. For our first example, I'd like to consider y equals the cube root of 1 plus 4x, and I want you to find y prime or dy dx. All right, so if we look at this guy, this is actually two different functions. There's an outside function, which is the cube root of what's on the inside, which I'll call u for now. And then the u on the inside is 1 plus 4x. So we've got the u is the outside function, and then we've got the inside function, 1 plus 4x. And so therefore, of course, u, the cube root of u is actually u to the 1/3 power. So if I want to find y prime, I'll take 1/3 u to the negative 2/3. All right, so that is the f prime of u, and then I'm going to multiply that times 4, which is the g prime of x. And of course, u we just said is actually the inside function. So this is faithful to what I said up here. It's f prime of g of x times g prime of x. Of course, I don't want my final answer to have u's in it because the question's about x's. So I'm going to change this to 4/3 1 plus 4x to the negative 2/3. I started with x's. I want to finish with x's. We can also do it using the Leibniz way. So therefore, df du is 1/3 u to the negative 2/3. du dx is 4. Oh, that's exactly what this says right here. And we get, of course, the exact same answer. So with the chain rule, you want to work from the outside inward. So every single step you go, you start at the outside, and then you say, okay, I did the outside, let's deal with the inside. If there's an inside of that, you deal with the inside of that. So you can actually nest several chain rules, and let's do an example where we have a little bit of nesting going on. Next, I'd like to consider the function y equals the sine cubed of 2x plus 1. And the first thing to note is the mathematical convention. When we put that 3 right there, what we actually mean is that this is the sine of 2x plus 1 cubed. So notice this 3 right here goes all the way out there. So you have to keep in mind that when the cube is there, it actually goes up there. And now to find y prime, all right, so we're going to work from the outside inward. I'm going to start and I'm going to hop my 3 down. And then I'm going to take the stuff on the inside. And it's going to get squared. The 3 hops down. I have a sine of 2x plus 1. So now I've dealt with the cube, I'm going to focus on the inside of this guy. Well, the inside of this is the sine of 2x plus 1, whose derivative we know is going to be the cosine of 2x plus 1. So I've now dealt with the yellow parentheses, and I've now dealt with the white parentheses, and I still have to do yet another set of parentheses. Chain rule is 2. So working from the outside in, the cube hops down, blah, 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 squared. Then we focus on the inside, sine, so that's derivative is cosine of stuff on the inside, and then the chain rule of the inside. So the chain rule can be repeatedly nested. I'm not going to nest it 12 times in a row. Certainly, you could do that. The secret to the chain rule is to work from the outside in and to do very careful bookkeeping. You have to keep track of where you are, where's the outside, where's the inside. Sometimes there'll be a product rule inside of your chain rule. Getting crazy. But before we consider that, I want to show you one other example with e to the x. So I'd like to consider the function f of x equals e to the 3x. And this may not look like two separate functions, but I'm going to rewrite this as e to the x cubed. So e to the x is on the inside, cubed. So if I want to take the derivative of this guy, the 3 is going to hop down. I'm going to get e to the x squared. And then I have to take the chain rule of the inside, which is another e to the x. Because the derivative of e to the x is itself. And you'll notice that this is 3 e to the x cubed, aka 3e to the 3x. And this is a simple version of a more general rule, which is to say that if we have e to the power of f of x, for any function f of x, not necessarily this function, so e to any function power, e to any function is going to be exactly what you started with times the chain rule of what's up here. So the rule for e to the x, we had just the simple e to the x rule. Well, that was only with e to the x. We can open it up, and now it can be e to any power. E to any power with x is going to be e to the f of x, which is exactly what you started with, and then you take the chain rule of what's upstairs, the derivative of what's upstairs. Let's do one more example employing this guy right here. So our last example for this section is going to be y equals e to the power x squared plus 2 plus 5x to the 4th power. So notice that this employs our rule we just talked about, e to some function. E to some function. So the derivative starts off with exactly what we just had. So copy down right away. E to the x squared times 2 plus 5x to the 4th power. I now need to take the derivative of what's upstairs. I need to take the derivative of this guy right here. But that's two things multiplied together. So that's going to require the product rule inside of our chain rule. Ah, okay, well, all right. So let's get that going. So derivative of the first times the second plus the first, so derivative of the first times the second plus the first guy, and now I need to take the derivative of this second guy. So let's do that. So I'll do the derivative of this second guy, which will be 4 times 2 plus 5x cubed. But there's something inside of here as well. I have to multiply times 5. So derivative of the first guy times the second guy plus the first guy times the derivative of the second guy, 4 hops down, 2 plus 5x cubed, and then the chain rule of that, which is 5. Notice, of course, that this 5 is only getting multiplied by the part that has the chain rule. The 5 is not getting multiplied by the first half because the 5 comes from the derivative of the second half. So you don't want that 5 on here, you only want the 5 over there. And I, of course, am completely okay with leaving it like this. If, however, you really like to simplify things, e to the x squared times 2 plus 5x to the 4th power times 2x times 2 plus 5x to the 4th plus, that's 4, that's 20x squared, 2 plus 5x cubed. And of course, this whole shebang is the chain rule derivative of this guy. So this whole guy gets multiplied by that. The chain rule really just requires lots and lots of practice. You just have to get used to working from the outside inward. And sometimes you have to work inside that. And sometimes there's a product rule inside the chain rule. And sometimes there's a chain rule inside your product rule. And it can get kind of crazy. This really just takes lots of practice. So we're going to spend 2 whole days in class practicing this chain rule because it comes up all the time and it takes lots of practice. And you're going to need to know how to do this in order to do derivatives for the rest of the semester. So there it is, the chain rule. We'll get lots and lots of practice, and I'll see you in class. Have a great day.